Good afternoon, everyone. This is Asitha from Cal State San Bernardino. First, I would like to thank the Data Science and Machine Learning Committee for giving me this opportunity to present the paper towards optimizing performance of machine learning algorithms on unbalanced dataset, which is done under the supervision of Professor Zhang at CSUSB. So this would be our sorry, I'm trying to go to the next slide. Just having some issue with the screen. Okay, got it. Sorry about that. I had a disturbance with the screen. So this would be the agenda for today. We would first start off with what is our problem statement and what are the existing methods to solve it. Next, we'll be looking into the proposed system and the data set chosen to prove it. And also following that, we'll be seeing the implementation and the performance evaluation. And finally, concluding it and what are some advancement in the same line. So to know the problems associated with imbalanced dataset, let's understand what is imbalanced dataset. In general, a dataset having huge number of records for one class and comparatively less number of records for other class is called imbalanced dataset. And in order to measure this, we use a metric called imbalance ratio, which is the sample size of majority class to the sample size of the minority class. With this kind of data, we mainly face two problems. One is the classifier learned from skewed data. So what happens in this is machine learning models are designed with the assumption to learn from balanced classes or a relatively equal number of instances for each class. When an unbalanced data set is fed to these models, the learning curve for majority class is high compared to the minority class. And the model tries to assign majority class to the minority class while predicting the outcomes. And the next problem is the equal misclassification cost. These algorithms assign a equal misclassification error, that is false positive is often not desired, but less critical than the classifying an example from the minority class as belonging to the majority class, so-called false negative. In such cases, using a misclassification error does not benefit the learning of the model. So in order to overcome these problems, there are some existing systems which can be dealt either at data level or at algorithm level. At data level, we either increase or decrease the number of records by using preprocessing techniques like oversampling and undersampling. At algorithmic level, we implement something called ensemble techniques. So an ensemble technique uses multiple independent models or weak learners, which are either similar or different to make better predictions. One of the technique is bagging, where n training sample space are selected from the original dataset with replacement. Each sample is trained on different classification models and aggregated to predict the result. And the other one is boosting. A weak classifier is trained repeatedly until its misclassification rate decreases. It is done by increasing the weight of every misclassified observation and also decreasing the weight of correctly classified observation. Some of the existing papers to solve this are in the paper handling imbalanced data with SMOTE and random undersampling. The author compares how oversampling and undersampling imbalanced data affects the model performance. After conducting experiments, the author concludes that oversampling imbalanced data along with ensemble algorithm like random forest yields highest performance. And we have the second paper, clustering based undersampling, where the author proposes two clustering techniques to undersample the majority class. In the first approach, the majority class samples are grouped into clusters until the class imbalance ratio becomes 1. That is, number of samples in majority class will be equal to the minority class. Now, this centroid of the cluster are considered as the new data points for the majority class. Whereas in the second approach, instead of considering the centroid of the cluster, the closest point to the centroid from the cluster is considered as the majority class sample, which showed higher performance when compared to the earlier one. So in our proposed system, we use both oversampling and undersampling techniques to balance the imbalanced data set. We also implement genetic programming to improve the performance of the model by selecting best feature set. So it is done as follows. The minority class from the imbalanced data set is oversampled such that it becomes half of the majority class. And once this is oversampled, we undersample the majority class samples so that it equals in amount to the minority class samples. Once the data is balanced, we use Tomek-Links to remove any data noise from the balanced data set. And then we implement genetic programming to select the best features for the selected classifier. This diagram shows the pictorial representation of the flow where the imbalanced data set is first oversampled using the algorithm SMOTE, and then we undersample it to make it more balanced. Once this data is balanced, we use Tomek-Links to remove any noise from the data. The balanced data set is further divided into 60 and 40% for training and testing purpose respectively. As we'll be using distance-based classification models, we'll be normalizing the data using standardization. Once that's done, we then use genetic programming to identify the best features and train the classifier on it. We use test data to predict how well the model is performing and evaluate based on some metrics. So we'll be looking into each of the techniques used in this process. Oversampling is a data preprocessing technique where the minority class samples are either duplicated or synthesized to reduce the class imbalance ratio. One of the methods we can do is by randomly oversampling, but this creates duplicate or the desired number of samples will be mostly redundant. So one of the advanced technique is a SMOTE, which is called as synthetic minority oversampling technique, which creates new data points instead of duplicating the existing ones. So this algorithm is implemented as follows. First, a random sample is chosen from the minority class. For the observations in this sample, identify the k nearest neighbors. Consider one of those neighbors. We identify the vector between the current data point and the selected neighbor. Then we multiply the vector by a random number between 0 to 1. In order to get the synthesized data, we add this to the current data point. Next, we have undersampling. In undersampling, the records from specified class are either deleted or merged to decrease the number of records. This is usually applied to the majority class as the sample size is huge. Random undersampling technique deletes the records from the majority class based on some randomness. We also have Tomek-Link, which can be used to undersample and which also acts as a data cleaning method. It is a modification to the condensed nearest neighbors algorithm. So in Tomek-Link, we call Tomek-Links are pairs of examples of opposite classes in close vicinity. Let's say we have two observations A and B. In order for A and B to be Tomek-Link, they should satisfy certain rules. That would be A's nearest neighbor is B and B's nearest neighbor is A, and A and B belong to different classes. That is, A and B belong to minority and majority classes or vice versa. Removing such kind of pairs reduces the data noise. Next, we have genetic programming, which is one of the recent and evolving algorithm based on the theory of evolution. It can be implemented into any optimization problems. So we will be using this to find the optimal set of features for the selected classifier. A genetic programming can be applied to any optimization problem, and it can be divided into 5 phases as initial population, fitness function, selection, crossover, and mutation. Let's go through each phase. A set of individuals are initialized into a population. Each individual is a solution to the problem. An individual is represented by a set of variables known as genes. Genes are joined into a string to form a chromosome, where each chromosome acts as a solution to the problem. Next stage would be the fitness function, which determines how fit an individual is. The probability that an individual will be selected for reproduction is based on this fitness score. The idea of selection phase is to select the best pair of individuals to pass them to the next generation. In crossover phase, we create the offsprings by exchanging the genes of selected parents among themselves, and the new individuals are added to the parent set to form a new population. The crossover operator can generate offsprings that are very similar to the parents. So we use mutation operation by exchanging the value of some features in the offspring at random. These steps are repeated until the population converges or the optimal solution doesn't get any better. We will be using 4 classification models to test the proposed system, which are decision tree, logistic regression, KNN, and SVM. We'll be looking into each one of it. Decision tree is a supervised machine learning algorithm that uses rule-based approach to make decisions. It is used the dataset features to create yes or no questions and continually split the dataset until it isolates all data points belonging to each class. The aim of a decision tree algorithm is to form a condition on the features to separate all the classes in the dataset to the fullest purity. In order to measure the impurity of the node, we use Gini index, entropy, and information gain. Next, we have logistic regression, which is a parametric statistical model used only for binary classification. This model uses the likelihood function to estimate the weights of parameters by studying the training data to predict the dependent variables of new observations. Algorithms like gradient ascent are used to find the optimal weight vector that fits the likelihood function. We use a function called sigmoid function to convert this real value into a probabilistic value. Based on a set threshold value and obtained probability, the test data is classified. KNN is a lazy learning algorithm. It stores the trained data until test data is provided for prediction. It classifies new observations by considering its neighbors' classes. It uses distance metrics like Manhattan distance, Euclidean distance to calculate the nearest neighbors, which requires scaling of feature values to reduce any bias. The value of k plays an important role in this algorithm, as a smaller value of k makes the model sensitive to noise, and a larger value of k leads to data misclassification. SVM, which is a support vector machine, is a linear model that creates a line or a hyperplane which separates the data points into respective classes. The distance between this hyperplane and the nearest data point of each class is considered as margin. To perform better on test data, a hyperplane with the largest margin is preferred. If the data points are not linearly separable at lower dimensions, additional features are added to separate the values at higher dimensions, which is highly impossible to separate all the data points into respective classes. We use something called soft margin, where a small misclassification is allowed in training data while adding a penalty for misclassifying test data. In order to test this, we have used bank marketing dataset from UCI Machine Learning Repository. This dataset contains information related to direct bank marketing campaign, which is conducted by a Portuguese bank, whether the client has subscribed to a term deposit or no. In total, it has 17 features, out of which 16 input features are considered to client's demographic information, whether a client is contacted or not, etc. And the output feature says if the subscription is accepted or not by the client. Here is the instance of the dataset where y is the output variable and the other input variables like age, balance, housing loan, etc. This dataset has a total of 45,000 instances, out of which 39,920 belong to the majority class, where the client has not subscribed for the term deposit, and the rest 5,289 belong to the minority class, where the client has subscribed for the term deposit. We see that 89% of the entire data belongs to the majority class, and it can be considered as an imbalanced data set. So in order to implement this, we'll be doing the initial EAD. Features containing categorical data types are converted into discrete by using label encoding. And then we converted duration, which was in seconds to minutes, to reduce the range from 0 to 90. Once this data preprocessing is done, we have oversampled the minority class using the SMOTE class from sklearn library. We have used the sampling strategy to set such that the records become half to the majority class. Once this oversampled data is then used into random undersampler to decrease the majority class samples to that of the minority class, making 19,961 for both majority and minority classes. The entire balanced data set is cleaned using Tomek-Links class, which removed any imbalanced data or any data points. This balanced data set is divided into 40 and 60 on random for testing and training purposes. We have used standard scalar to normalize the data, prior which we have used genetic programming to obtain the best feature set for each algorithm chosen. We have used an estimator to set the algorithm and also scoring to check against which accuracy method. Here the graph shows how balanced the accuracy varied across different generations during the evolution of best feature set for a classifier. We'll be seeing what evaluation metrics are being chosen and how they have varied over different classification models. In this project, we will be calculating 8 different metrics for each classifier. Those are accuracy, balanced accuracy, recall, F1 score, ROC curve, area under the ROC curve, precision recall curve, and confusion matrix for each resample dataset and compare it with the 4 chosen classifiers. Accuracy is one of the commonly used performance metric which calculates the number of correct predictions over total number of predictions. When dealing with highly imbalanced dataset, accuracy is biased by majority class predictions. So a light modification to this is balanced accuracy, which takes the mean of majority class accuracy and minority class accuracy. Next, we have recall, which measures the ability of a classifier to correctly predict the positive class samples. It is also called sensitivity or true positive rate, given by number of true positives to the sum of true positives and false negatives. Precision measures the percentage of predictions made by the model that are correct, given by the number of true positives divided by the total number of positive predictions. Both recall and precision are combined into a single metric called F1 score, which is the harmonic mean of precision and recall. Its value ranges from 0 to 1, where a model with F1 score 1 can predict every single instance correctly. Next, we have ROC curve, which is a graphical representation of how well a binary classification model can perform across different classification thresholds. It is calculated by plotting recall on the y-axis and the corresponding false positive rate on the x-axis at different thresholds. Calculating the area under the curve gives a numerical value which is easy to compare. As precision and recall focus on the minority class Precision and recall curve gives better insights into the model's performance. It is plotted by taking precision on y-axis and recall on x-axis for different thresholds. At last, we have confusion matrix, which shows the overall performance of a model in a matrix form for easy interpretation. Especially for imbalanced dataset, it gives a clear understanding of how predicted values deviated from actual values for each class. We see the performance of each binary classifier by comparing the evaluation metrics. We see that on each classification model chosen, the proposed method performed better than the existing imbalanced dataset. Here we see that for decision tree, and this we see for the logistic regression. Though the accuracy is high for unbalanced data set, as we have discussed, it's because it's more biased towards the majority class. And we see that KNN has shown highest accuracy of 90%. And then we have support vector machines. So by comparing all the four algorithms, we can state that all four algorithms models performance drastically increased when trained on resampled dataset when compared to the original imbalanced dataset. This huge difference between accuracy and balanced accuracy for unbalanced data shows that the model is skewed towards the majority class, whereas for balanced data, both accuracy and balanced accuracy have relatively closer value. It can be concluded that by applying a combination of oversampling and undersampling together, along with cleaning and feature selection, has improved the performance of the classification models. In future work in the same line, we can design a model which leverages both data level preprocessing such as oversampling, undersampling, and also algorithmic level approaches like random forest or any bagging algorithms. By combining this proposed technique, we can also use genetic programming at feature level along with instance level. That is, select the best instances from the entire data set, which will count towards the performance. Or we can even make the data sets into cluster and choose the best clusters or optimal clusters using genetic programming. Thank you.